All right, so we are recording now. All right. So I think over Slack, there were some questions about flow space abstractions and confusions around it. So maybe we can take a step back and try to, make sure that we understand that all of us understand that very well before we proceed. Because, flow space abstraction is kind of like very basic and fundamental to software-defined networking. So it's worth spending a bit more time understanding these basics here. Okay. So like I can start by asking you folks and calibrating my expectations of what was conveyed, how much was I was able to communicate about flow space abstraction. So can anybody tell me any overview of flow space abstraction? What do you, or maybe a first order question is like, what is a flow? Can anybody explain me what is a flow? You can type or you can speak up. Either is fine. Okay. So yes, we need to revisit some basics here so that we can appreciate these concepts better. Yeah, sequence of packets. Yeah, I like that. All right. Okay, so you can see my screen. Let me adjust that a bit. Okay. All right, perfect. So we have A and we have B, right? And this is kind of like the basic fundamental of networking. Okay, so these are two end hosts, right? And suppose that A is trying to set up a TCP connection with B for some, or maybe I should call it an HTTP connection over TCP, right? So anybody can tell me what is the port number associated with HTTP protocol? It's called HTTP. 80, okay, port 80. So let's say A is a user and we can call it we can draw some laptop. It's a laptop, right? And then it is trying to communicate with the server B and it is requesting an HTTP page, and this is how the connection is set up, right? So the port here is 80 and then port here is some random port. Let's call it 3333, right? I'm just making this up. Okay. So if the traffic is coming from B to A, right, which is the HTTP, response message, right? So it will have a source IP of, oh, we didn't say anything about source IPs, right? So what should be the source IP? Can anybody tell me an IP address that belongs to Google? Yes. Let me make this easy. All right. So 172.217.14.100. Okay. Now you might be wondering, where is this coming from, right? What I did was I just ran a tool called ping.www.google.com, and this is the IP address that it resolved to, right? And it might not be the IP address when you're trying to download something from, or you're trying to establish an HTTP session with Google, but I'm just picking it up, right? And what is the IP address of A, which is, say, my laptop here at UCSB. So how will you, if you want to know your IP address, what will you do? So I'll put 169 dot. No, where did it go? 231 dot. It's too much of information here. Yeah, 222.1.1. Okay. So yes, IP config, IF config, depending on whichever tool you want to use. So this is the IP address that is right now my IP address, and that is the IP address that I resolved for google.com. And now I'm trying to establish a session, and or I'm sending GET requests, and the response is coming back to me for the packets that are belonging to this response. Then they will have a source IP, which is 172.217.1400, and source port will be 80, and the destination port will be 33333, and the destination IP will be 169.231.22.101, right? Okay, this is clear. And what is the transport protocol that it will use most likely? TCP. What are the other options? And this is just a knowledge test for 176A. Okay. Beyond TCP, UDP, anything else? Possibly SMTP, yes, possibly, but I was more like, well, maybe not SMTP. SMTP is an application layer protocol. So from transport perspective, I was thinking of hearing about QUIC. So QUIC is a transport protocol that is also getting a lot of traction. So anyway, so these are the protocols that you can use, and TCP and UDP are the most likely ones that you will be using. But for HTTP, we're talking about in most cases, in most sane cases, it's going to be TCP, right? So it requires a reliable transport, and that's why HTTP is mostly over TCP. Okay. So anybody knows what is the value associated with the TCP? Like if you're looking at the packet headers, and if you want to look at the protocol field of the packet, what will be that value if it is TCP? Six? Anybody? No. Okay. So proto value is equal to 6 for TCP. It is equal to 17 for UDP. Okay. So typically a flow is a sequence of packets that are associated with a 5-tuple in most cases, right? So or basically it's just an abstraction for grouping different packets, and 5 tuples is the most convenient or most intuitive way of visualizing flows. But I don't think that is a hard and fast rule that it has to be only these 5 tuples, but 5 tuples is the most commonly set of tuples that are used to identify a flow, right? So we are talking about 5 tuples where we have source IP, source port, destination IP, destination port, and proto, right? So when you are looking at the packets, you will look at these 5 set of fields, and if they are same, or for all the sequence of packets that have the same set of fields, then you classify them into one flow, right? And intuitively, when you're getting these packets, so it is very hard, especially if the response message is quite big, it is very hard to put all the information into just one packet. So a flow mostly engages or entails sending multiple packets in the network, and all these flows that share the same 5 tuples can be termed as belonging to the same flow. Okay. Is this part clear? Do we have any questions or confusions around it?
I'm sorry, what is proto?
Proto is protocol. So what is the transport protocol which is used here? And that is part of the header fields that we have in the packet.
Okay, thank you.
Yeah, I'm sorry, I'm using a shortcut here, but yeah, proto is protocol, transport protocol. Okay. Okay, so let's try to open this up a bit more. So when we talk about a laptop, that is, my laptop, and assuming that it is connected over the wireless interface here. So this laptop is wirelessly talking to an access point, right? And this access point will be connected to, any suggestions? What should this access point be connected to? And I'm sitting in, HFH. Okay, I'll complete and then we can, like later revise that. So most of these access points will be connected to a building level router that we have in most of the buildings on campus networks, right? So when you think of all these access points on campus networks, they're all connected to a routing device or a router at the granularity of these buildings. And then all these building routers are connected to a core router. And for redundancy reasons, it's not just one core router. There are, like 2 or 4. I think at UCSB we have 4, but I might be wrong. Like, this information gets updated all the time. But for simplicity, let's assume that there are 2 such, like core routers to which each of these building routers is connected to. Now, to communicate with the internet, we need a specific type of router and we need a specific protocol, right? So can anybody tell me which routing protocol is used for inter-domain routing? Any guesses? What routing protocol is used for inter-domain routing for exchanging, forwarding routes to a distant internet remote location? BGP, yes. So Daniel answered BGP. That's the right answer. That BGP, which stands for Border Gateway Protocol, that is the protocol that is used for advertising, forwarding routes in the inter-domain settings, right? So when we say inter-domain settings, we are talking about, like UCSB is an AS, is an autonomous system AS that has its own set of prefixes that are assigned to it. And then UCSB will advertise to its neighbors that what are the IP addresses that are reachable within its network. And then its neighbors will advertise to, other neighbors. And that's how this route propagation or this information exchange happens across the internet. And that's how everybody in the internet knows how to reach UCSB, right? So UCSB, I think, like most of these enterprise networks do have multiple providers, but the most common or the most used provider, I think, is called Scenic. And Scenic is, like an educational network. And Scenic has like basically UCSB and Scenic have peering relationship. So BGP, like UCSB's border gateway router advertises all UCSB IP addresses to Scenic, and then Scenic advertises all the internet routes to it. And that's how UCSB knows how to reach Google, and Scenic knows, and Scenic's peers and everybody else knows how to reach UCSB, right? So let's call this a border router. Let's call this a core router. Let's call this a building level router, right? And then Scenic, as I was saying, is, like we can, generalize and say like it is connected to public internet. And in the public internet, we also have, Google sitting somewhere, right? And within Google, we have some server that has the IP address, which we are using here, right? Okay. All right, so far things are clear. Okay. So now, like, if we want to write a policy, right, and maybe we, UCSB IT folks bought a new middle box or a new network device, which specializes in some, like state-of-the-art scheduling policies to optimize the quality of experience for video streaming services, right? So let's think of it as some optimizer that is sitting at the border router. And like it is maybe it is specializing for some YouTube optimization, right? So, UCSB is committed to provide you a better quality experience for YouTube videos because all our lecture videos are posted there. I'm just kidding. But it is possible theoretically. There are a lot of commercial tools out there that are used for optimizing different type of quality experience, metrics for different type of video streaming services. So let's assume that UCSB bought one, and UCSB wants to make sure that all traffic coming from Google, or maybe at least one specific prefix from Google, is going to this middle box or this optimizer. Okay. So for simplicity, let's assume that it has identified that all traffic that is coming from this prefix, which is a /24 prefix, so it will be 172.217.14.0/24, right? So all these /20, all traffic coming from this prefix is YouTube traffic, right? It's not true. I'm just saying assume that, right? So now if you want to write a policy which says that all traffic that is coming from this source should be sent to this optimizer, right? And now this is a rule that we want to write with an open, as an open flow rule, or for assuming that this border is an open flow switch, right? So what do we do, right? We have to use, or what open flow suggests is that we should be using a match action abstraction, right? Maybe I should write here, match action, right? This is what we were learning about the other day. Okay, this is okay. So it will write rules that will first match on some specific traffic and then apply that action, right? So action is clear that whenever there is a match, it wants to forward traffic to this optimizer, right? But what should it match? So what can a policy be? A policy can be that we should match on a specific flow, right? So the policy can be that I only want to optimize the performance of this specific IP address, right? Serving YouTube traffic from this specific IP address, right? And I also am very specific about the flow, which is defined by the combination of all these 5 tuples that we have identified. So this, as the destination port, 80 as the source port, this is specific IP address, this is specific IP address as the, this is the source IP, this is the destination IP, right? So I can specify a flow based on these specific 5 tuple fields, right? And I can write a rule which says match on all these 5 tuples and then forward the traffic to this optimizer. What it will do is that it will only send a specific flow to this optimizer, right? And that is a very, very specific rule that I have expressed for this match action table, right? Now, if I want to be a bit more lax and say okay, no, I don't want to benefit only this flow. I want to benefit, or I want to optimize all flows that are coming to this IP address from this IP address and this port, right? So let's write it down a bit. So the first rule that I was saying will be match and source IP equal to 172. Destination IP equal to 169.231. And source port equal to 80, and destination port equal to 3333, and proto equal to 6, right? So this is a specific rule, match that I will match expression that I will write, and I will say forward it to, let's say that this is port 1, this is port 2, this is port 3, right? So it will say forward to port 2. Okay, is that clear? Are there confusions here? Okay, I'm assuming that you folks are following what I'm saying, but if you have any confusion, feel free to stop me. So this is a very specific rule which is only targeting a specific flow, right? And now and when I say specific flow, then all packets that have these 5 tuple fields in their header, they will match to this rule. And this is a specific action of forwarding to port 2, which is the TCP optimizer port that will be applied on the packet, right? But now I want to be a bit more, broader in terms of who benefits from this optimizer. Then I would say that, okay, I want to benefit all users that are in the same /24 prefix, right? So this IP address that I have 169.231.222.101. So this is my IP address, right? But if I do /24, then this is all IP addresses that share the same prefix. Like, first 24 bits are the same. The last 8 bits can be anything, right? So I can change this rule. So I should be specific here. It was 222.101, right? So I will change this rule, and everything else will remain same, but destination IP will be 169.169.231.222.0/24, right? And then all other fields are exactly the same. So if I write this, oh my bad, sorry. So if I write this less specific rule, then I can specify the I can have this entire subprefix. But I think like somebody pointed out a very good point that I forgot about destination port 333 rule, right? So what this rule that I have written here, rule number 2, let's call it rule number 2. What it will do is that it will benefit all these IP addresses that belong to this prefix, but only for a specific port, which is 333. And it is possible because this, like when you're talking about these specific services, then the port number, the lower port number is decided based on the application type, but the higher port number is kind of like randomly selected. So it is possible that none of these IP addresses will have that 333 as the destination port, right? So it might not benefit anybody. So yes, you are right. I think, Garrett, that the first thing that I want to remove from this generalization is that I want to remove this destination port equal to 333. Like if I do that on the rule 1 itself, then it will apply to all flows that are coming to that specific IP address, right? And if I remove that and write a /24 rule, then it will apply to all IP addresses that belong in the prefix from where the traffic is coming from a specific Google IP address. Okay. And again, I can write another version of this rule where I can say 172.217.14.0/24, which is like all prefixes that are 172.217.14.0/24, right? So this is the prefix. This is the all set of IP addresses that belong to a specific prefix within Google, right? Google owns that, and then I'm trying to optimize, or I'm trying to send all traffic coming from this prefix to my optimizer. So I can modify this rule where I can specify that source IP is 172.217. Maybe I can be well, let's keep it simple. Okay, so source IP now, this is rule number 3. Sorry. Okay, and the source port is still 80, so which is focusing which is still targeting port 80 traffic or HTTP traffic coming from this prefix, going to going to this prefix, coming from this prefix, right? And this policy can be applied there. Okay, so the bottom line here being that there are these different type of packet fields. So it is .0/24. So basically it is representing all IP, or all set of IP addresses that belong in this prefix. Okay, good. All right. So the bottom line being that, we can group a bunch of packets based on these 5-tuple fields, because there is a semantic meaning associated with these group of packets, right? So all these packets are coming from the same process. When I say 5-tuple, all these packets are coming from the same process on the end host, right? So that is the most logical way of thinking about packets, or sorry, about flows, that all these packets that are associated with the same end-to-end connection, same process, are grouped as one flow, right? But now you know, like if you start writing policies based on one flow, then there will be too many rules that you have to write, right? So it makes logical sense that if there are multiple flows that have to be applied the same policy, then you want to group those flows, right? And that is what you will do, you know, by writing less specific rules. You know, like, so the rule 1 is the most specific rule because it is pointing to a specific flow, right? The second rule is relatively less specific rule because it is, you know, like capturing or covering the entire set of /24 prefixes, both for destination IP and source IP addresses, right? So this, you know, like OpenFlow supports match action table. Like, you know, it leverages two abstractions. One of how to look at the packets in a flow space, right? So it comes up with the flow space abstraction. It argues that packets, you know, like can be grouped as flow, or the flow is the most meaningful way, or is the finest granularity at which you can specify a particular rule or identify packets in the network. Because if you say, like, you know, like it might not make a lot of sense writing two different policies for packets that belong to the same process, right? So I see very, like, you know, like logically it makes no sense to write a policy which says, like, you know, for first packet apply, or for first 10 packets apply rule 1, and for the remainder of the packets apply rule 2. So that is something which didn't had as much operational value. So, you know, the abstraction that people came up with was like, okay, let's think about the granularity at which you know, we can have some meaningful ways of expressing these rules, and that came out to be the granularity of flows defined at the granularity of 5 tuples, right? So again, I'm repeating myself that 5 tuples is logical, but that is not the only way, right? Because you can keep on adding more fields to it to define a flow rule, but this is something which is kind of like the most meaningful way of expressing, or the finest granularity, but still meaningful, right? And then if you want to, you can group bunch of flows and write fewer number of rules, right? Especially if you are going to apply the same action on those group of flows, right? So you know, like IP addresses are naturally, like, you know, can be aggregated naturally. It's very natural. Destination port, source port, not so much, but you can still write, you know, like you know, like you can still express the prefixes, or you can specify a certain set of bits that you care about, certain set of bits that you don't care about. So you can write them as bit vectors, that what you know, like how you want to match on specific fields here. Okay, so is this part clear? Is this helping us understand the flow space abstraction? It is helping us understand the match action abstraction. Like, you know, match action not so much, because I'll try to explain that a bit more. But to understand the match action abstraction better, it is important that we understand the flow space abstraction. So is the concept of what is a flow? Like, you know, flow is a group of packets identified based on 5 tuples, and then, you know, bunch of flows can be grouped together depending on the semantic requirements that we have. So I hope this part is clear. Then we can move on to the discussion about the match action tables and match action abstraction. Okay, all right, cool. All right, so now I'll do a quick shift to our presentations. So Steven asked, what is a flow space? So I think that's a good question. Maybe we should continue, like we should have that concrete discussion, right? So you understand what is flow, right? And flow has, like, for simplicity, let's assume that, you know, 5 tuple is the only way, or is the only way for expressing or identifying a flow. Can we agree on that? Okay. I'm waiting for an answer. Can we agree on that? Yes. Okay, perfect. So when we say 5 tuples, then we have 5 dimensions, right? You can, like, you know, basically then flow is a vector which has 5 dimensions: source IP, destination IP, source port, destination port, and protocol. For each of those vectors, there are different number of values that these fields can take, right? So source IP has 32, like, is a 32-bit field. So it can take 2 raised to the power 32 different values. You know, similar with the destination IP, source port and destination port will also have 16 bits. So they'll, like, you know, take 2 raised to the power 16 different values. Same with the destination port. And protocol, I forgot how many bits it has, but I think it has 8 bits. I might be wrong on that, right? So, those many number of values it can take as well, right? So now we have this massive 5-dimensional space. Any point in that space will be a flow. Okay, because any point will have a specific value for each of these dimensions. It will have a specific value for source IP, like we have in this example. It will have a specific value for the destination port. It will have a specific value for source port. It will have a specific value for source IP and a specific value for proto, right? So that will be like, this flow that we discussed earlier is a point in that 5-dimensional space. Is that clear? Okay, so, and now when we so we had some discussions, and I'll get back to the slide soon. So we had some discussions about, defining some, planes or some structures within that flow space. 5 dimensions visualization is going to be tough. But, if you basically, if you don't care about any specific field, right? So if we say don't care about, well, it's kind of tough, right? So let's think about what is a line, or yeah, 5 dimension. I struggle to visualize things. But I think if we simplify and just have 2 dimensions, I think that was the exposition reason why we were just showing with 2 dimensions, because it's easy to reason. But if we fix the, say, destination IP to a specific value, right, then all the flows that are coming in from this specific IP address, right? So let's try to have that discussion clearly, right? So let's talk about this IP address 169.231.222.101, right? So when we talk about this destination port, source port, destination source IP proto, then that is one flow. But if I am just looking at the destination IP 169, then all flows that are, where this IP is the destination IP, are the ones that can be, basically these are group of flows, right? So if I'm just matching on, or if I'm just looking at this 169, then we have this really massive group of flows that are associated with this IP address, right? So what does that mean in 5 dimension? I can't really tell you. But if I'm just looking at the source IP, destination IP, then that will be one line, right? If I have maybe 3 dimensions, then that will be a plane. Beyond that, I don't know. I'm not that smart. But is that making the concept of flow space clear, that it's a 5-dimensional space because we are defining a flow as a vector defined by these 5 dimensions of 5 tuples? Okay, that's good. That's what I want to hear. All right. So let me now get back to our slides, lecture slides. That should be one. Okay. All right. I think we had a better discussion on this. So let's talk about the match action forwarding abstraction, right? So the biggest question was that, what is the right abstraction that one should use for the forwarding data plane, right? And in general, match action was the most obvious abstraction one, because it was a bit legacy abstraction as well, that the previous set of generations were also focusing on match action, that match on some fields and then apply that action, right? So that is the match action abstraction, right? So the previous generation of these switches, they had a very specific, they had hard coded that what fields you can match on, right? The action primitives are more or less the same, but what fields you can match on was, very, very hard coded in the previous generation of hardware targets, right? So say, for example, some of them will only allow you to match on destination IP. That's it, right? Some of them will allow you, like, will be more generous and maybe let you allow, like, allow you to write rules that can match on destination IP and source IP both, right? Very extremely or very small resources will be spent on rules that can match on all 5 tuples, right? What OpenFlow was suggesting is that, abstraction wise, we should have no restriction in terms of what combination of fields you can match on. And that was very powerful because it was providing you this extreme flexibility that you can write very fine-grained rules for applying your network policy, right? So if I can only match on destination IP, then I cannot write a policy which is saying that do something different for HTTP traffic, right? Because to identify flows that belong to HTTP protocol or HTTP traffic that are HTTP traffic, I need to match on the source port, right? But if they don't allow me or they don't give me the flexibility to match on that port, then I cannot have those type of policies implemented, right? So this is an example of what was different about the match action abstraction that OpenFlow was proposing, right? So match action table or match action abstraction already existed, but the only difference was that it didn't restrict on this set of fields that you can match on. So it offered incredible flexibility in terms of these match rules that you can write or the match expressions that you can write for the hardware or for this programmable switch. So match action forwarding was like, there is a packet coming in with some header, and then you have a table, right? So match action table. Match, it will search for these expressions in the header field. And, like if the header is H, so it will match on H, then whatever is action specified for this header will be applied, right? And then it will lead to some transformation of the original header and the packet will go out. So, the action primitives here are forwarding. So it can be as simple as like, okay, forward to a specific port. They can also be used to push or pop header fields, right? And they can also be used to decrement some bits in the header fields or just drop packets, right? And I'm sure that some of you might be curious to hear, like, what does push and pop really mean? Where is it used? Like, why do we need it, right? So as simple as that. Anybody wants to take a crack at that? Like, what is push and pop of header fields really mean, or what are the applications here, or what can be potential applications here? So my question is that, I'd say that there are these 2 interesting action primitives called push and pop, right? So push header Y after bit 12, pop header bits 8 to 12. Like, what do you think can be a use case for this? Okay, one answer is change the direction a packet is headed. Yes. Analyzing the network. Okay, fair enough. So I would argue that, this can be used to support packet encapsulation, right? So there is a packet coming in. If I want to support any new protocol on top of the existing packets, right? So I would basically push new set of headers on that packet, like, apply simpler policies in the network that only match on this new header that I have pushed on top of the original packet. And then once the packet is leaving my network, then I can pop those special headers and then let the original packet go, right? So this might sound familiar to you when you think about VPNs, right? There is this GRE encapsulation in that case. You also, like, we also briefly discussed something about network virtualization that we will revisit again, that when we want to provide this abstract view of the network and we want to apply abstract policies, then we need some type of virtualization layers. And you can think of this as as a mechanism that can support virtualization. That if I want to apply policies that are applicable only to the virtual network, what I can do is that push a new header, which is which is useful or relevant to this virtual view of the network, apply those virtual changes, or apply changes to that virtual network. And then when the packet leaves, then I just pop out that header and then let it go as the original packet, right? So we will discuss that more later, but I just wanted to, comment a bit on what is the use of these push and pop primitives that we have in the action fields. I actually don't know. I can answer that question by looking up. I don't know the answer to that. I don't think that is how the IPv6 packets are encapsulated in IPv4, but I might be wrong. But that's a good question. All right, so moving on, it is possible that we might have complex set of policies out there which we might not be able to express in just one table, right? So what the researchers and practitioners came up with was that rather than forcing these switches to just support this one table abstraction, we can split it up into multiple tables, right? So let's think about it more logically, right? I was talking about 5 tuples, right? And if we have this 5 tuple abstraction, or if we want to express policies that match on any combination of these 5 tuples, and if I just have one table, then let's reason about how many maximum number of rules will I require in worst case. Okay, so let's do some basic maths. Tell me, how many bits are in total required for these 5 tuples? Any answers? I'll repeat myself. So we are talking about these, we have been talking about these 5 tuples. Can you tell me how many total number of bits are required for expressing all these 5 tuples? For example, source IP requires 32-bit, destination IP requires 32-bit, proto requires 8 bits, destination port, source port requires 16 bits each. So what is the total? 104, right? That's simple. So if there are these, 104 bits that, that are required to capture this 5-dimensional flow space that we have expressed, then the maximum number of rules that can be there in one single table can be 2 raised to power 104, right? I don't know what exactly that number is, but it's huge because, that's like billions and trillions of rules that are required, right? That's prohibitively costly for any implementation to have those many number of rules if we want to match on these number of flows, right? So what these practitioners came up with was that a lot of time you might not have policies that are, concurrently applying this on all 5 fields, right? Like maybe some of them will require matching on source IP, destination IP, and some of them might require matching on the destination port separately. So if we break them, so if we write a table which is matching on source IP, destination IP, and then another one which is matching on destination port and source port, or maybe we don't want source IP, destination IP together, we want them separate. So depending on the type of requirements we have in terms of flexibility, we can break them down into multiple tables, right? And that can save us from this requirement of explosive number of rules that we might require. We might be able to break it down, and when we break it down, then we might be able to reduce the number of entries, match action entries that we require in this table to satisfy or to express our policies, right? So this is one intuition for match action table. And when OpenFlow first came out, then they were just pushing plain and simple things out there. So they just supported a single table abstraction on the first go, and that was very problematic because it required a lot of rules, and especially if there were two rules that were overlapping with each other, and if you just have one logical table, then applying both rules was very hard. And especially if you want to apply both rules and reason about the priorities of those rules. So that was very hard for OpenFlow in general, and over time they came up with this advancement in the newer versions of OpenFlow where they supported these multiple match action tables. So here, when we have a packet which with like two different set of fields in the header part, first it will match on H1, apply that action, and then it will match on this like HN, and then apply that corresponding action and move out. So so far we have talked about the basics of software-defined networking. We talked about that software-defined networking is all about extracting simplicity with finding the right abstractions. And we talked about different type of abstractions and how they were realized, right? At least we talked about one instance of how they can be realized. We haven't really talked about the entire spectrum of realizations that we will cover later. But I just want to give you a short history of software-defined networking, and this is relevant to some of the questions that you folks had, that how much of this is just some researcher cooking in their lab versus something getting real, right? So this entire journey kind of like started a while back, 2003, 2007. This was the time when like the dot-com bubble just had burst, and then things were again heating up and new services were coming in. Companies like AT&T, like the internet service providers, were very dominant players. Internet was very, very popular among the common user. Like the internet subscription was just mushrooming all across the country and all across the globe, right? So around that time, a lot of work started happening because people realized that to support these flexible or complex network management policies, we are just like increasing the complexity of the network itself, and things that we were discussing before, right? Like people were just focused on mastering complexity, which meant that networks were breaking all the time. These networks were getting a bit unreliable, and people like this was we don't want to companies like AT&T, they didn't want to sell a plan and then have users really frustrated because they can't connect to the internet or the service that they want on a regular basis, right? So this was something which was of high importance. The other thing was that all these companies, when we think about mastering complexity, they realize that like this problem can be solved by buying trillions of dollars worth of hardware and like pushing that into the market, right? But then that that's not how economics work, and putting so much of money to solve the problem was not sustainable, right? So they had to come up with more principled approach and think about how these problems can be solved. So during this 2003 to 2007 phase, a lot of solutions came out, but most of them didn't argue about changing the existing hardware or changing the existing like devices that we use or something very fundamental. They were more of a band-aid solutions, right? So they were like, okay, let's use whatever we have, but on top of it, let's build better control abstractions and programs that can help us configure these existing complex devices more effectively, right? So they didn't get rid of this distributed, or they didn't come up with this distributed state abstraction. They just said like, okay, we will work with it, but we will collect all the information at some other remote controller and then apply those distributed algorithms up there and simplify the configuration of these devices, right? So one work which was very dominant that came out in this phase was RCP, remote control protocol program. I forgot the full like name of it, but RCP was a paper that came out from AT&T, and it had like people who are now very famous networking researchers and professors. So Jennifer Rexford, who's head of department at computer science at Princeton. So she was one of the main lead on this work at AT&T. She was then a researcher at AT&T, and Matt Caesar and Nick Feimster. So these are all big names in networking, and they were all like part of this problem on how can we simplify network management with better abstractions. And then 2008, these ideas about that people had about finding better abstractions for control plane got materialized into basic set of principles that people wanted to focus on. OpenFlow came out around this time period, and OpenFlow, as we know, is a realization of a forwarding abstraction, right? So it is not OpenFlow is not SDN. OpenFlow is an instantiation of one of the abstraction that is required for SDN, but OpenFlow came out, and it was also supporting like all these research groups are also, very particular about making sure that they're solving specific use cases that are of interest, not only in academia, but also in the industry, right? So they created an ecosystem where a lot of work that was done in the academic world was also getting pushed out in the real world, right? And the network operating system, as we have learned that network operating system is very critical for providing this distributed state abstraction. That is something that was developed. Like the operating system was called Knox, and this was this was incorporated or like part of this company called Nicira. Nicira got acquired by VMware. So I don't think the acquisition happened in 2008, but Nicira I think was created around that time frame, right? And in 2011, people realized that the open source community has to be better organized to make sure that we have maintenance of all these tools, and we have this proactive maintenance of all these tools, right? Because every research group was creating their own set of tools which had a very short shelf life, right? So if I am a researcher, I will push something, say like this is the best in the world, and then I graduate, and then it's lying out and nobody can use it, right? So basically they realized that we need a bit more consistency in terms of how these tools are developed and offered and maintained over time. So Open Networking Foundation came out, and then it was supported by all these organizations that I have listed there. And I think like the software-defined networking got very real by that time, 2011. I would say it got very real. And there are these two research papers that also came out around that time frame, which like maybe a year or two later, but like similar time frame that we're talking about. That these companies started realizing that there is a huge opportunity by embracing the principles of software-defined networking in their own network, right? So they started contextualizing that what does software-defined networking mean for them, how exactly it solves different problems that they are facing right now in terms of making these networks more reliable, scaling with the higher demands. So there was a lot of adoption of SDN principles in all these big companies, especially when we talk about Google and Microsoft. They were early adopters of these SDN principles, right? And around 2013, this protocol independent switch architecture idea came out. And we'll talk about it in more detail as we move forward. But the key idea was that, before 2013, people were still buying, people made all the innovations in the control plane abstractions and everything, but they were still relying on silicon that were old generation. And, they were not really as faithful to the new set of abstractions that were out there in the control plane. And they were kind of like becoming a restriction in terms of how fast we can come up with new use cases and come up with new applications. So this work on protocol independent switch architecture basically identified those problems and came up with a real solution to that problem. Again, this paper came out in academia, like from Stanford University, but then it was also taken forward into a company called Barefoot, which maybe I mentioned briefly. And then Barefoot recently got acquired by Intel, right? So this is just a kind of like overview of how different things evolved over time. Before 2003, 2007, networking was all about mastering complexity. 2003 to 2007, there were a lot of protocols that came out which were focusing more on coexistence, which is let things be as they are, but on top of it, we will provide some band-aids and make sure that we are able to manage them more effectively. But then 2008 was more drastic, let's rethink this networking problem completely differently. And then 2011, things got more serious in terms of how they can be commercialized and offered to a broader set of community rather than just big players using it. And then 2013 was, I would say, a very big game changer in terms of the hardware switches that we use for software-defined networking, right? And we'll talk about it more as we proceed further. So before we go to the next set of slides, I just want to make sure that we have this clear takeaway with us that layering is a good abstraction, which was a big enabler in making internet a huge success, right? But it is only for data plane, and it does not simplify or help a lot with network management. It helps a lot with like realizing it, implementing it in the data plane. Before SDN, networking focused only on mastering complexity, and mastering complexity is unfortunately not the same as extracting simplicity. And we can extract simplicity by coming up with better abstractions. And software-defined networking offers 3 key abstractions that are very critical: distribute state, specification, and forwarding abstraction. I'm reiterating these points because these are going to be critical from quiz perspective. So very, like if you have questions, confusions, this is a good time to ask them before we move forward. No, I think everybody's clear, right? All right. So I'll move to the next set of slides that I have for you. Give me one sec. Did anybody had a chance to look at the quiz yet? So can you see a slide with lecture 3 as title? Yep. Okay, perfect. All right. So I think like you can realize that we are running a bit behind in terms of whatever the original schedule was. But I think it is important to spend some time on flow space abstractions and everything else. So I think we are fine. It's important to learn well than learn too much in this course. So as long as we are like all clear on the basic fundamental concepts here, we're good. Okay. So in the next set of slides, I'll be talking more about the programmable data planes. I think we can skip recap because we just talked about it. But what are the learning objectives here? So in this set, we'll be learning what are the different type of data planes. Like they're mostly, are this software data plane or a hardware data plane? And also what is the difference between the fixed function data plane and the reconfigurable data plane? So before I ended the previous set, I talked about PISA, protocol independent switch architecture. So that is very relevant to this discussion about fixed function versus reconfigurable. So PISA is a reconfigurable data plane, and before that, what we had was fixed function. What are fixed function forwarding pipelines? What are the limitations? What is PISA? What do they really offer? Right. So this is going to be the set of objectives, learning objectives that we will be focusing on. So we know that in software-defined networking, separation of control and data planes is very fundamental, right? Software-defined networking is all about separating, taking these control plane elements from these devices, making them dumb, having a network operating system, which offers, a simplified abstraction to the control applications, and then control applications work on that graphical view of the network and apply their policies, right? So the data plane can be hardware as well as software, right? So the blue ones that you see are obviously switches. These are hardware switches. These are based on specific application-specific ICs or integrated circuits, ASICs that we call, and these are custom designed for packet forwarding. And like if you recall, we were earlier saying that a switch has 2 CPUs or 2 brains. One is for control logic stuff, and the other is for handling the packets. So the handling packets is the one which is fast but dumb, and is specifically designed for handling packets, right? But we also have software switches, right? So with these new data centers out there, there is this, we have the virtualization for the compute. The virtualization of compute requires running, it decouples computing from the physical server, and you can have the virtual machines for compute. And the virtual machines, they had these requirements that to handle the networking within the physical server, we need some type of virtual switch inside that physical server, right? And that's what the virtual switches are for. And they provide networking, servings or offerings within that physical server that is running multiple virtual machines. So now let's talk about the software or the virtual switches. And one of the most popular instantiation or realization of virtual switch is called Open Virtual Switch, or OVS, right? What it does is that it is providing packet forwarding service for the virtual machines, and supports these flexible policies that we want to apply in context of network virtualization or data center networks, where we have these virtual machines associated with different type of applications, right? In fact, these virtual machines can be owned by different tenants. So you go to AWS, you can set up your own VM, and you are a different tenant compared to someone else who's spin their own VM on the same physical machine, right? So you might be two different tenants running on the same physical server running a VM site. To provide the network connectivity, we require certain flexible policies that can be supported, and that's what we need this virtual switch for. And we can write those old CLI commands to manage these switches, or the connectivity services for these switches, or we can use OpenFlow to manage them, right? So OVS is all about the next generation, new generation realization of a virtual switch that is controlled by OpenFlow. Let's dig deep into that, but I should keep an eye on the time here. So we don't have a lot of time. I'll see how much we can cover, but I don't want to rush here. So if you have questions, just let me know, for what we have covered so far. Don't hesitate to interrupt here. This virtual switch uses OpenFlow protocol to communicate with the network operating system, right? And if you recall, the OpenFlow protocol is basically you can think of that as a southbound API, right? That connects the network operating system with the physical data plane, right? And in this case, that data plane is implemented in the user space. So now the question is, why Open Virtual Switch, right? So if the consider this setup, right? So we have these two set of physical servers, and they are running these different type of virtual machines. The color coding here is that the yellow one belongs to one tenant, one type of service, the green one belongs to one type of service, and blue one belongs to a different type of service, right? We have this virtual switch, and we want these physical servers are sitting at two ends of the continent. Maybe one is sitting in New York, the other is sitting in LA, right? So if you want to provide this seamless connectivity between the blue VMs or the green VMs or the yellow VMs, then we have to provide this virtual connectivity or virtual abstraction, right? So if I'm writing a policy, I don't really want to worry about the public internet over which this traffic is going to go through, right? So what we can offer here is that we can use network operating system that manages this entire set of devices, and it can use OpenFlow to configure that if the destination is remote, then use encapsulate this packet using IPsec, and the backbone that is carrying this traffic will just focus on this encapsulated packet and make sure that it is able to reach the physical destination, and then at the physical destination, the packet can be decapsulated and sent to the VM as required, right? So in some sense, this type of functionality simplifies managing virtual machines for multi-tenant data centers, right? So as I was saying, right, we can have multiple tenants sharing the same physical machine, and these VMs can be on different physical VMs that belong to the same tenant can be on the different physical machines, but to provide a seamless connectivity, right? To provide this one hop, an abstraction that all these VMs, even though they're running on different physical servers, they're in principle just one hop away, right? So those tenants don't have to worry about, oh, how will I forward my packet from this physical server to a server that is in New York, right? From LA to New York. So like the abstraction that we are offering is that they don't have to care about it. For them, it's just local network, right? For them, it's like, okay, forward to this VM and the packet just goes there, right? Under the hood, we have this encapsulation principle in place, and all that can be orchestrated by the network, by a control program that is getting the abstraction for network operating system, and that is using the OpenFlow protocol to configure the rules on this virtual switch, right? So what is an open virtual switch? Okay, some question. So OVS makes servers appear like they are on the local network. Yes, so when you say servers, basically the VMs, right? So it can provide an abstraction, and this is the virtualization aspect, right? So the virtualization can provide an abstraction that all these VMs are just like logically next to each other in the same subnet. Did that answer your question, Garrett? Yep. Okay, perfect. All right, so what is an open virtual switch? So it's a multi-layered software switch. This is something which kind of like started as an academic project, but then it because there was a lot of interest in the industry as well. So there was a cross collaboration between industry and academia, and the implementation was production quality C implementation, which is publicly available, right? And it supports multiple virtualization technologies like Zen, KVM, VirtualBox, whatever you say. Like it is compatible with most of these virtualization techniques. And talking about the key components, so one of the most important component is the kernel module that is responsible for handling the packets, right? So one way of looking at it is that when we talk about these switches that are or the data plane that are responsible for handling packets, they have to be fast and dumb, right? If you process something, if you process packets in kernel supports very limited functionalities, right? So it is more flexible than an ASIC, but it is still very, very constrained in terms of what type of compute capabilities or what type of programming features or APIs it exposes you to, right? So I don't know how many of you have written a kernel program in the past, but if you have, then you know that it is not the you can write it in C-like language, but or C language, but you don't have access to all the libraries that you typically have in the user space, right? So it's a very constrained, restricted environment where you can write a program. So this OVS mod.ko is the kernel module that is core to the Open vSwitch implementation. It is an example, it is a good example of fast but dumb module, right? So it can process packets at much faster rate, but it cannot have a lot of flexibility in what type of how it handles packet or how it reads packets, what type of policies it can apply. It is very dumb module, right? But it is fast. And then so basically it is taking in the packet from the machines or host network interface card. The packets go to this kernel module. Kernel decides which is it going back to the original NIC? Is it going to a different NIC? All these decisions the kernel is making. But this kernel is then connected to different virtual machines using a virtual NIC, right? So if the packet has to go up to a particular virtual machine, then it will forward to that virtual NIC. If it has to go back, then it will forward to a physical NIC, right? So all these type of forwarding decisions have to be made by the kernel module. But it is controlled, this kernel module is controlled by OVS switchd, or you can think of a virtual switch daemon that is implemented in user space. So this one is relatively more flexible. This is the one that is kind of pushing rules into the kernel module of precise rules that have to be implemented. There are these specific algorithms for matching on packet headers and applying the actions and policies in place. But there is a limited amount of space or state that these kernel modules can maintain. There is limited flexibility on processing that it can do. But all this virtual switch daemon that is sitting in the user space is a bit more flexible one. And this is connected to a VSDB server. So, OBS database is basically, this is an implementation that is, you can think of it as a database that is used for storing, less frequently changing activities about the network, capturing the state of the network, but not so frequent ones. This OBS, vSwitch-D is, there for quickly changing the flow rules or handling packets in general. And then this vSwitch-D is communicating with or is controlled by the network operating system, and they use the open flow protocol for exchanging information with each other, right? Like in some sense, the network operating system is using open flow to push the type of rules, and also it is also communicating through the database to query the state of the network so that it can expose it to the control program, right? So we will dive into each of these modules in a bit more detail in the next lecture. But I think hopefully this should give you a good sense of what an open vSwitch is, why do we need it, and where does it fit in context of software-defined networking, right? I guess the time is out, so I won't hold you for any long time. But if you have any questions, I'll be more than happy to answer right now.